Okay, anyway, let's start with lecture number 3. And yeah, so I want to start talking about orthogonal projections. And this word you usually do not find in the book for machine learning. But as someone coming from the mathematics side, what they call normal equations is actually exactly talking about orthogonal projections. So let me recall what we talked about. So we were talking about linear regressions. And what was the scenario? So we had some test data T and with X values and Y. So we had this example with the Tebasaki, where X, the features were given by the weeks living in Nagoya, and Y, the labels described the number of Tebasaki eaten. And then we plotted these data points and saw that they looked like fitting a line, but they are not exactly on a line, and we wanted to find the best possible fit for this. We wanted to find this hypothesis, and but let's assume that we have these data points which are actually on a line. So if I have 3 points, and let's assume that they are on a line, so this would mean that these data points here, I have y1, here I have y2, and here I have y3. And if this would be the case, then this blue curve here, this hypothesis, this line through these 3 points, which was given by this theta 0 plus theta 1 times x, then these two numbers, theta 0 and theta 1, would satisfy this equation here, right? Because here, if you multiply this out, then here you have exactly h theta of x1 up to h theta of xn, where here in the picture n equals 3. But of course, this is not the case in reality. So this equation here, so maybe let me do this smaller, and let me call this here the matrix A, and this here the vector y, and this here the vector theta. So in this perfect world, we have this equation that A times theta equals y, or in other words, A theta minus y equals 0. But in reality, we have a different picture. So maybe in this case, the data points, maybe I have these 3 points. Let me make them red. This, this, and this. And then in reality, the best, what we want to find is this here. But in this case, these thetas, they do not satisfy this equation here. So in this case, we have that A theta is not equal to y. But I mean, how do we find this nice line here, which somehow is the best line we can find? Well, what we try is we want to try to make this here small. So instead of bringing it to 0, which is not possible, we at least want to try to make this small. And what does it mean to be small? Well, this here is a vector. So this is a vector of size n. And so if we want to say something is small, we need to use some norm. And in this case, what you usually use is the Euclidean norm. So what is the norm? So recall the norm of a vector. If I have a vector v1 up to vn, then the Euclidean norm of this is just I take the entries. Each entry I take the square, and then I sum them up, and I take the square root. So in this case here, we cannot solve a linear system, but at least, so this here we cannot solve, but we can try to make this difference here from the left and right-hand side small. Okay. So this is the same slide with the text which I just said. So usually our data is not exactly on a line, but we want to minimize this norm of this matrix times this vector here minus the right-hand side here. And the goal today is to explain the following result, which you saw last time, but which is maybe not clear. So the statement is that if we want to find the theta such that this here is minimal, what we need to consider is this new equation here. So if so here the left-hand side is the transpose of A times A. So this here is a square matrix. In this particular example, this here is, well, this here is A, theta, and this is Y. And what is A transpose times A, where this is, I have this matrix here. This is the transpose of A. And I multiply it with A. So in the result, if I multiply a 2 by n matrix with the n by 2 matrix, the result is a 2 by 2 matrix with some entries you can calculate. So this here is a 2 by 2 matrix. And this vector here, this theta, in this case here, is a vector of size 2. And here the right-hand side, we multiply y. So what is A transpose y? So A transpose is again this matrix here, x1 up to xn. And y is just our y. So if I multiply this 2 by n matrix with this n by 1 matrix, or this vector of size n, so this will also be a vector of size 2. So here it's really, the statement is that if I want to find the best possible solution to this equation here, which maybe doesn't have any solution, but we want to find the best possible one, the statement is that we can solve this linear system here with 2 equations and 2 variables. And this in general has an exact solution. So here we really have a 2 by 2 matrix multiplied with something we want to find equals a vector of size 2. And this usually has an exact solution for theta 0 and theta 1. And these theta 0 and theta 1 then will give the best possible solution to this equation here. So this is the statement of this theorem. And the goal today is to prove or to understand the statement of this theorem, because if you see it like this, maybe it's not clear why the exact solution of this linear system gives the best possible solution of this linear system. And this here is in the literature also called the normal equations. Okay, so let's try to prove this theorem. So you don't need to understand why now, because this we will try to understand. So for this, we need to recall some words from linear algebra. And yeah, so this actually my students in linear algebra 1 now learn this week. So already first-year students can now follow. So if I have a matrix So we will do it now a little bit more general, not just a theta of size 2, but more generally. So our matrix A will be an n by m matrix. And I'm sorry, in the homework, we use m times n matrices, but I want to use an n times m matrix here because n usually corresponds to the number of trainings examples. So if I go back here, the size of this vector, this n, corresponds to the number of trainings examples. So that's why I use a n times n matrix. And the m usually in our case will be d plus 1, where d was the number of features. But yeah, just don't be confused. So usually you would talk about m times n matrices, but I wanted to use the same n. So don't worry. Anyway, if we have a matrix, an arbitrary matrix, then the image of this matrix A is the following set. So this is an n times n m matrix. So the image will be a subset of the Rn. And this is the set of all vectors V such that there is a theta such that A theta equals V. So in other words, if I have a fixed matrix A, then this linear system here, A theta equals Y, has exactly a solution if this Y is in the image of A. So this is the definition of the elements in the image of A. It's just, if I have a matrix, the elements of the image of A are those vectors I can have on the right-hand side of a linear system, such that this linear system has a solution. So let's do an example. If I take, for example, the matrix. So here in this case, m equals n equals 2. So what is the image of this matrix A? So it will be vectors of size 2 with a certain property. Well, for which vectors can I solve this linear system here that AX equals V? Well, here we see that the first, the second row is just 2 times the first row. So no matter what I multiply here to this matrix, theta 1 and theta 0 and theta 1, the result will also have the property that the first entry is half the second entry. So the image of this matrix here is all vectors v1, v2 with the property that v2 equals 2 times v1. So if I take a vector of this shape, then I can solve this equation ax equals this vector. Okay. So let's draw this image. So what is so this here is the image of A. So this is a subspace of the R2. So these are all vectors which satisfy the property that the second entry is twice the first entry, right? So for example, here I have this vector 1, 2. And this is in the image of A. And clearly I can find vector x such that ax equals 1, 2. Right? Because what is the solution of this? In this case, the solution is, well, it's not this direction, but so if I take the vector 1, 0, then A times this vector x gives this 1, 2. But if I have a vector which is outside of the image, so let's say this one here. So let's say this is y, which is 3, 1. then this equation ax equals y, so this has no solutions. So maybe let's, so this has no solutions. Right? Because here this vector is not in the image of A. But now, what would be the best possible solution? Meaning, how can we minimize this ax minus 3, 1? So what should this here be? So this here is in the image of A. What should we use such that this difference here is small? So in other words, which point on this purple line here is the closest point to this point here? Well, the answer is this point in this case here, because what we want to do is we want to take the orthogonal projection to this line here, because every other point here would have a larger distance to this point here, right? So in this case, yeah, so in this case, oops. So in this case, this quantity here, so which is, so this green part here is exactly this line here. So this is minimal for this point here. And this point is this 1, 2, and therefore we get the minimal, this is minimal for the case x equals 1, 0. Okay. But let's do it more generally, or maybe first do a little bit more complicated example. So let's consider this matrix here. And now also let's think about what this has to do with the original problem of finding best fit. So if I draw again this, and I have the points 1, 2, and 3, 1, 2, and 3, and I have h theta of x equals theta 0 plus theta 1 times x, then this equation here, a theta equals y1, y2, y3, has a solution if and only if this vector here is in the image of A, meaning that if I start here with y1, y2, let's say I take these 2 points, then to have a solution like this, this means that these 2 points already dictate where the next point needs to be, because 2 points already give me a line, and therefore this point here, y3, is already dictated. So in this case, you can also say that the image of A, I mean, this you need to do some calculation to find out that the image of A are those vectors y1, y2, y3, such that if I choose y1 and y2, like here I choose this and this, in order for this to have a solution means in this graph here that the third point is also on the same line which is given by these 2 points. So in this case, if you do some calculation, you see that in this case this y3 needs to satisfy it's minus y1 plus 2 times y2. Okay. So in this here, is a subset of R3. And this we can also plot. So here, so this is the R3. This is our matrix A. And here is the image of the matrix A. And if we plot all points in 3 dimensions which satisfy this equation here, then we get this plane here going through the origin. Okay. And yeah, and if we now, for example, want to solve the equation that A theta equals, let's say, 3, 0, 0, where is 3, 0, 0? Well, here it's 1, 2, 3, 0, 0. So here is the vector 3, 0, 0. So this here is clearly not on this blue plane, and therefore this has no solutions. But in this picture here, and we will do this later, the calculation, what we want to do now is also, like in the example before, we want to take the projection of this point onto this plane, and then this point on the blue plane, this we can put here on the right-hand side and find a solution for this theta, and this corresponding theta will then give us the best solution to this original equation here. Okay. Are there any questions on this part so far? Okay, then let's continue. So now some words you also learned in linear algebra. So if you have a subspace, like this plane or a line going through the origin, and the image of a matrix is always what you call a subspace, then you can define the so-called orthogonal complement of this subspace U. And this is defined by taking all vectors which are orthogonal to all vectors on this subspace. And this here is a dot product. And this is, if I have 2 vectors with entries U1 up to UN and V1 up to Vn, then the dot product of these 2 vectors is just a number. And this is just given by multiplying U1 with V1 plus U2, V2 up to UN, Vn. And then this has some geometric interpretation, namely the statement is if the dot product of 2 vectors is 0, then these 2 vectors are orthogonal, meaning that, well, this picture I can just draw in 2 dimension or in 3 dimension, but this just means that the angle between them is 90 degrees. So therefore, this orthogonal complement of some space, if I have a plane, then the orthogonal complement is just everything which is orthogonal. So if I have a plane in 3 dimensions, then the orthogonal complement is just a line. So maybe if we go back to this one here, then in this picture, this here would be the orthogonal complement of the image. So we could write here, this is the orthogonal complement of this image of A. And in this picture here, the orthogonal complement would be somehow this thing here. So this should be a line. Or maybe it looks more like this. So this here is the orthogonal complement of the image of A, which is just this line being orthogonal on this blue plane. Okay, so maybe some of you remember this from linear algebra. And now the statement is, which is actually quite a silly statement, that if I have a subspace, like the image of a matrix A, then any vector in this space, no matter if it's on the image or not, can be written as a sum of something which is in the subspace plus something which is in the orthogonal complement. So for example, in 2 dimensions, if I have some subspace U, then the orthogonal complement is maybe, well, not really, but here. So let's assume this is 90 degrees, then this is the orthogonal complement. And the statement is that any vector y, this vector here, can be written as something in U, but here I can take this vector and I can take this vector here. So here, this is what I would call yu, and this I could call y orthogonal. And then you see clearly this vector here is the sum of this in U plus the stuff in the orthogonal complement. And this yu is called the orthogonal projection of y onto U. Because you see this difference here is in the orthogonal complement, meaning if I start with y and then this yu here is exactly what I get by going to U. And this point here is exactly the point on U which has the smallest distance to this point y, because all other points are farther away than this. Okay. And this is what we want to, and this is what we want to find, because in our application, this U will be the image of A, and then this Y will correspond to our data, our labels, and we want to take the orthogonal projection here to find something in the image of A, and if we have something in the image of A, we can find some theta such that A times theta is this thing here. And then the corresponding theta will also give us the best fit for our original Y. Yeah, so this is the question: how do we find the orthogonal projection? So so let's draw this again. So let's assume we have now a matrix A, and we have the image of A, which is a subspace, and we have a Y. So what we want to find is this here, so the Y, the orthogonal projection of Y onto the image of A. But actually, we do not want to find this point. What we want to find is the corresponding theta. And every element in the image of A is given by A times some theta. So actually, we want to find an element which we can write like A times theta. So A times theta is in the image of A, so this will give this point. And this is actually what we are interested in. We are interested in this theta. And now, what if we consider this one here, A theta minus Y? Well, where is this in this picture here? This is exactly this here, right? If I take this point here and I subtract this, then I get this guy here. But this here is now in the orthogonal complement. So this is in the orthogonal complement of the image. Yeah. So now our problem is, given A and Y, we want to find a theta such that A theta minus Y is in the orthogonal complement of the image of our matrix A. So we want to know how the orthogonal complement of our image of A looks like. And there's a quite simple description, namely, maybe I can copy it this. Copy. The statement is, if I have a matrix and I'm interested in the orthogonal complement of the image of this matrix, then this is the same as the kernel of the transpose, where if the kernel, well, these are just fancy words, but the definitions are quite simple. So these are just all vectors v, such that A times v equals A transpose times v equals 0. And why does this has to do with the orthogonal complement of the image of A? Well, if I have a matrix A, which is given by some columns, M. So here, if I have an n times n matrix, then this matrix A has m columns. And the image of A are all possible linear combinations of these columns. So this is the span of these columns. But what is A transpose? Well, A transpose means I just take the columns as rows. And what is the kernel of A transpose? Well, these are all vectors such that if I multiply this vector with this matrix here, then I get 0. But if I multiply here a vector, if I multiply what I do here, so if I multiply AT with some vector, well, let's say V, then the entries here are just given by taking the dot product of this vector with this. So here it's exactly C1 dot V, C2 dot V, and so on, Cm dot V. And the kernel are those vectors V such that this is 0, but this means exactly that this V here is, that all these entries are 0, and this means that this V is orthogonal to all these columns of C. So oops. But then you see that this is the same as the orthogonal complement of the image. Because the image is spanned by these vectors, and if the kernel is given by all vectors which are orthogonal to these vectors, then this is exactly the orthogonal complement. Okay, so the statement here is, by this proposition, the orthogonal complement of the image of A is exactly the kernel of A transpose. So let me copy this. Are there any questions here? No. And in a second, we will have exactly the equation we were looking for. So the original problem is we have a matrix A and a vector Y. We want to find a theta such that A times theta, which is something on the image, such that the difference here is in the orthogonal complement, because then this is the nearest point to this Y. But now we also saw that the image, the orthogonal complement of the image, is just the kernel of A transpose. Therefore, we want to find theta such that this is in the kernel of A transpose. And being in the kernel of A transpose means if I multiply it with A transpose, it's 0. Therefore, if I multiply this with A transpose, then this is 0. But if we just multiply this out, we see that this is 0, but this is the same as A transpose A times theta equals A transpose Y. So this is the equation we had at the beginning, and therefore we see if we find a theta which satisfies this condition here, then this theta, if we multiply it with A, will give the point on the image of A which is the nearest point to this y, and therefore this difference here is minimal. And therefore we get our original thing. Therefore we get exactly this statement here. We want to find the best possible solution for this unsolvable system here, but we can do so by solving this thing here. And this usually always has a solution, an exact solution. And maybe this answers the original question at the beginning for the homework 1, because in the homework 1, you should solve this equation here exactly by using this implemented NumPy solve. And then you get an exact solution, which gives the best fit for this one here. Okay. Yeah, and maybe just one final comment. So far, we just had these examples where the data is near a line, but of course, there could be also data which looks like this. And then maybe the best fit would be a polynomial. But even though the name is linear regression, this doesn't mean that we can just fit something which is linear. This just means that these coefficients are linear in some sense. So this we can also, so if I have some x1, x2, and so on, then I can do the same game by just taking the matrix A. So instead of putting just x1 here, I use more columns and also maybe allow x1 squared, xn, x1, oops, d, and here xn squared up to xnd. So this red curve here, we can then write like this. So we are looking for thetas, theta 0 plus theta 1, x1 squared, theta 2, no, sorry, x squared plus theta 2, x and theta 2, x squared, up to theta d, x d. So this linear regression, this word linear here just means that the coefficients here are linear, but the features, they can depend non-linearly. So you can have something non-linear here. So and this is also part of so this is part of the homework that you use the stuff we discussed before for these more general matrices. And of course, you can also, instead of polynomials, you can use a logarithm or square roots or some other fancy functions. But still, what you do is use linear regression to get these coefficients. Yeah, and now I wanted to switch to the homework and go through this. Okay, can you see this? So this is homework 1. So you can find a link on the homepage, but also in the Discord, and you just need to accept it with your GitHub. And so this, because of last time, there were some complaints that this was too much code for beginners. So here we really start at the beginning and have some explanation how to deal with matrices. And your first exercise is to, so here's an explanation how you could write a function which adds two matrices. And also how to deal with some exceptions. And the first exercise is that you write a function which calculates the transpose of a matrix. So you need to use these concepts here. So here you can learn how to use these for loops, go through the columns and rows, and this you should use to write a function which get as an input the matrix A and then returns a new matrix which is a transpose. And then the next part would be to implement the multiplication of two matrices. So of course, everything here is already implemented in NumPy, but to just get used to this Python, maybe this is one good thing to do at the beginning. And then here's also one example how to solve a linear equation. So for this, you can use this implemented function of NumPy, this linear algebra, oh, not this one here, to solve a linear equation. So maybe I just skip over this. So if you have questions on this now, you can ask. And then you should use all this to do what we just discussed. So you want to find, given a matrix A and Y, you want to find the best possible solution. So maybe this equation AX equals Y doesn't have or A theta equals Y doesn't have a solution, but you should write a function which gives the best possible solution. And inside this function, what you need to consider is this linear equation here. And this linear equation has an exact solution. And this you can solve by using this function here, this linear solve of NumPy. So the task here is I give you a matrix A and Y, and then you need to build these matrices A transpose A and the right-hand side here. And then this you can use inside this function here. Okay. And then you can do some plotting. So here's again the Tebasaki example. This is just plotting the data. And then the next exercise is to write the function best fit, where as an input you get data, the X values, the features, and the Y values, the labels. And then using your best solution function, you should find the best possible theta. So in this case here, you should have an output theta 0 and theta 1. And so what you need to do here is you need to take these data here and write them in the matrix A and Y, and then use your best solution method and then return the theta. And then you can also plot the H, the hypothesis you can get out of your thing. So here you don't need to do anything. This is already using your best fit function, but you need to implement this best fit function here. And then a bonus would be to do it generally for polynomials. So instead of just this simple theta, which is a linear function, you should do it for a polynomial. And therefore, instead of taking as an input X and Y values, you also take as an input the degree of the polynomial. And of course, this function is also implemented already in NumPy. So this is polyfit in NumPy with the exact same input. But the idea here is that you use your own functions and implement it by yourself. So the only thing you use here from NumPy would be this function, this linarc solve. But if you want to go completely 100% self, then you can also implement this linarc solve by using this Gaussian elimination. And then in this case, you would have a 100% your own implementation of this function without using any functions from the library. So maybe this is a good exercise to get used to Python. And then the next exercise, maybe next week or a little bit later, will be more towards machine learning and gradient descent. But maybe for those who are not so familiar with Python, maybe this is a good start learning this a little bit. Are there any questions on the homework 1? Maybe the person with the question at the beginning.
Oh, it's fine. I just read the homework wrongly.
Okay. Okay, then I will go to the iPad again. Good. So yeah. And okay. So now next section. So what we did now, this linear regression, and there are also a lot of variants of this linear regression. So this part here of the supervised learning. And what we want to do now is give one example of classification. And confusingly, the name of this algorithm is called logistic regression. So it's also some kind of regression, which is actually here, but it is used to do so-called binary classification, so to decide between the two things. So don't get confused. We are here in classification, but the thing we are talking about is called logistic regression. Okay. So what is the main idea for binary classification? So maybe one standard example you could think of is a spam filter. So if I have emails and I want to decide if they are spam or not, there are just two possible outcomes. It could be just not spam, or it could be spam. So it's not like it's 50% spam. It's either it goes into your spam folder or it goes into your inbox. So therefore, our label space, which we denoted y, is now just a finite set, which we usually use a 0 and a 1. And the example we will talk about will be this passing exam example. So for example, the feature could be hours studied for an exam, and the labels could be that either you failed or you passed the exam. So it's also 0 and 1. So it's not like you can pass 50%. It's either you passed or you didn't pass. And so here you can see some training set. So again, one asks some people how long did they study, and then some of them tell you either they failed or they passed. And so what we want to find now is some decision if, so we want to find a hypothesis such that if I enter again a new number for hours of studying, which then tells me if this possibly, if you will pass or not. And of course you could do this. So what graph do you have in mind here maybe is that here at some point around here, we switch from not passing to passing. So maybe it looks something like this. But of course, here are some points which doesn't really fit. So maybe it's not like this. Maybe it's a little bit more like this, or maybe like this. But we could also say, well, why don't we just use linear regression, right? Because we could also take a graph here and then say maybe everything above 0.5 is passed and everything below 0.5 is failed. But there you already see the problem that, for example, if we would add another point here, then maybe the best fit curve would go more in this direction. And if we add even a point here, then it would go like this. And then you already see that this doesn't really fit this data here. And also, this graph here goes above 1 and it goes into the negative value. And maybe also a polynomial would not really be the best solution here. So really what we want to find is really a curve which looks something like this. So this curve, so the hypothesis will not be just between, so it will not just give 0 or 1, but we will try to find a curve like this. And then we say it's passed if it's above 0.5 and it failed if it's below 0.5. Yeah. And this kind of function is called a logistic function. And this is why this algorithm we want to explain, or this method, is called a logistic regression. And So there are various choices for such a function, but the most common one, for several reasons, is the so-called sigmoid function, or also called logistic function. And this is given by this function here. So s of x is given by 1 over 1 plus e to the minus x. So what property does this function have? So you can see a plot here. So for example, at x equals 0, if I plug in a 0 here, then this is 1, and therefore this is 1/2. So one property is that s of 0 is 1/2. So what happens for big X? So if X goes to infinity, s of X, well, this is calculus 1. So what happens if e to the minus x goes to infinity? Well, then this goes to 0, and therefore this here goes to 1. And if x goes to minus infinity, then the value here goes to infinity, and therefore this whole thing goes to 0. So like you see in the picture here, it's really between 0 and 1, and in the middle it's 1/2. And we want to find some variant of this function with some parameter to fit this data here. So you see already this looks like this s of x, but here is not 0, so it will be at a different point, and also we want some factor to make it wider. Yeah, so therefore, what is the model for the hypothesis in this new method? So recall in the linear regression, the hypothesis we chose had this shape here. We had d labels, x1 up to xd, and we multiplied them with these weights. And so this notation I didn't use before, but so the weights are elements in rd plus 1. And therefore, if I multiply, and also recall these x, the features are also in rd plus 1, where we x1 up to xd had this convention that x0 is always 1. And with this notation here, this theta transpose times x is just, well, theta transpose is theta 0 up to theta d times this vector x1, x1, xd. So therefore, if you multiply this with this, you get exactly this here. And you could also say this is just the dot product of theta and x. So this was our hypothesis in the linear regression case. And now in logistic regression, what one does is one usually takes the same hypothesis, but plugs it into this sigmoid function. Okay, so this will be the new hypothesis. So it will be some sigmoid function, but inside we have this this original hypothesis. So it will be these. So for example, in the case d equals 1, this h sigma of x will be 1 over 1 plus e to the minus sigma 0 plus sigma 1 x. But more precisely x1. So this here is x1. Okay, so somehow this theta 0 here and the theta 1 will tell us where the sigmoid function, where this point here at 1/2 is. I mean, when is this 1/2? This is 1/2 when this here is 0. So in this case here, this h theta well, in this special case, at this point, oops, it's 1/2. Okay. So, but now, so the next thing we did in the linear regression case was to define the cost function, because at this point we ask ourselves, how do we decide if the parameters or the weights thetas are good or bad? And then we defined this function j, which was given by the sum over all trainings examples, and then taking the difference of the hypothesis at some trainings feature minus the trainings label, and then took the square. And then we said we want to minimize this function. But now we will do it a little bit differently by using the so-called maximum likelihood method. And for this, we need to say what we mean by likelihood. Oh, but first I do some example. Oh yeah, I also did the D1 case here. So again, this is a D1 case for our hypothesis. And for example, in our trainings set with these hours of studying and passing the exam. So for example, if you choose minus 10, 1 for these numbers here, then you get this line here. And for example, minus 3 and 1/3, you get this line here. So you somehow see that you can vary how wide this logistic regression function gets. So maybe it gets wider when there's even more overlapping data here, but maybe let's assume we don't have this thing here, then maybe the best possible thetas would give something really steep. But the question is now, how do we define, how do we find these theta 0 and theta 1? And so how do we say that thetas are good or bad? And how can we find good thetas? And for this, we will now talk a little bit about probabilities. So our hypothesis is now a value between 0 and 1. So we can also think of this as being some probability. So there's some, if you study such and such hours, then the probability of passing the exam is something between 0 and 1. And maybe some of you did some basic probability in school, also at university. So there's this notation PAB, which is called the conditional probability that the event A occurs given that event B occurs. So in our example, this A will correspond to passing the exam, and the event B will be such and such hours were spent on studying for the exam. So our hypothesis, which we want to find, we can view this as telling us the probability, this one here, the probability of passing the exam. So maybe I could also write it like this, P pass exam, the probability of passing the exam when we studied X hours. So the probability of passing the exam, assuming that we studied X hours, is exactly what this function h theta should give us. And here, this notation, so this y equals 1 is just the label being 1 means passing the exam. Here we mean X is we studied X hours. And here it's just that this, I mean, this probability now depends on this parameter theta, because this function h here depends on this theta. So this is just a notation. And then clearly with this, the probability of failing, so here y equals 0 means failing, is, if we want to use the function h theta, is given by 1 minus h theta. Because if the probability of passing the exam is 30%, so it's 0.3, then the probability of failing the exam is 70%, so it's 1 minus 0.3. Okay, so this is really just a notation, but it's important now that we can interpret this hypothesis as being some probability of failing or passing. Or in this case, we say this h gives us the probability of passing the exam. And this here we can now put in a closed formula, which is given like this. So our y, our value, our label, sorry, can be just 0 or 1. And so if you want to put these into one formula, one simple trick is just to write it like this. So we take we take h theta to the power of y times 1 minus h theta to the power of 1 minus y, because if you plug in 1 now, then this is just h theta to the power 1 times 1 minus h theta x to the power 0. So this here is just 1. So this is just h theta of x. And if you plug in 0, where then the first term vanishes, because it's a power to 0 here, and here it's just 1 minus theta. So it gives the same formula as above. Okay. And so now comes the word likelihood. So what we want to find is the best possible theta. And in general, if you want to find the best possible, so if you have given training data, then you want to ask for a given weight, a given theta, how likely is this theta the best, how likely does this theta fit to the training data? So the likelihood, if you look it up, it means it measures the goodness of fit of a statistical model to a sample of data. So if you have training data, then we want to ask what is the best possible, so what they call here statistical model. In our case, this is a theta. What is the best possible theta, which corresponds to our training data? And in our case, so it will be a function where we plug in theta, and then it gives back how likely this theta is the best possible fit to our sample of data. And since our hypothesis measures the probability, so if we have the likelihood of some theta, will be just given by the product of all probabilities over the training set. Yeah, so more precisely, if I have a training set T, where we have some data, like hours of studied for the first person, and well, maybe he failed, and then hours of person studied, the hours studied of the second person, and he failed, and so on. And here maybe this, the last person passed. Then the likelihood that theta describes these data in the best possible way is when the product of all these possibilities are, well, the likelihood is given by the product over all possibilities here. So meaning if these thetas are chosen in such a way that this describes this data well, then these probabilities are high, because if I plug in some training example here, where I know this person studied such and such hours and he passed or failed, if this theta is chosen correctly, then this probability is high, because then it fits the training starter. And if we take the product over all trainings example, this means that we assume that all these things appeared at once. So yeah, so I mean, if you ask for the probability of two events appearing at the same time, you multiply the probabilities of these two events. And this is exactly what we do here. So the likelihood of our weight theta is given by the product of all probabilities. And this is what we want to, so we model these probabilities by this hypothesis. So we ask for which theta is this function here big. And this is why we want why it's called the maximum likelihood. So we want to find the theta with the maximum likelihood. Okay. Okay, no questions so far. And so here again is a formula from the slide before. So it's a product over all probabilities. And these probabilities were given by this closed formula, including our hypothesis. So we want to maximize this. And usually what you consider, so usually these likelihoods are given by products of probabilities. And often it's easier to, instead of maximizing this product, it's easier to maximize the logarithm of this product. And this makes sense because the logarithm is it's monotonically increasing. So if you apply it to some function which you want to maximize, then also you can also maximize the logarithm of this function. And the nice thing is, or the point why it's easier, or one point is that the logarithm turns these products into sums. So if we apply the logarithm to this function here, which is called the log likelihood of this weight theta. So if you apply the logarithm to this product here, then product becomes a sum, and exponents, I mean, this is hopefully clear that if I take the product of these rules from school, and if I have a power here, then this is just c times the log. Therefore, if you apply the logarithm here, you get a sum, and these exponents become factors here. And here we just have the logarithm of our hypothesis. So therefore, the goal will be to maximize the log likelihood here, meaning we want to find theta such that this sum here over all training examples is big. And this we will do by gradient ascent. So in linear regression, we want to minimize something. We want to make something small. So in this case, we wanted to use this gradient descent of our cost function. And for this, we calculated the gradient. And then the gradient showed in the direction of the steepest ascent. So we went in the other direction. So we subtract something from the current position where we are. So we started with some random theta. And then in the first step, we looked in which direction shows the gradient. And when choosing this learning rate, we moved in the other direction. And then we did this several times. And then at the end, we get some theta, which is near the minimum. But now we want to maximize something. And therefore, now we use the gradient ascent, which is the same idea. But now we want to go uphill. So if we start with some theta and then look at this point, what is the gradient of the log likelihood? This will show in the direction where this log likelihood will go up. And then we also go in this direction. And therefore, we will have a plus here with some training rate. And this we will do explicitly next time. So what we need to do this, we need to calculate the gradient of this thing here. So we will need to plug in, what was the gradient? So the gradient was given by this vector where we have this partial derivatives here. So we need to consider what happens if we take the derivative of this function here. And for this, we need to plug in our hypothesis. So here, our hypothesis was given by 1 over, maybe let's do again the d equals 1 case, 1 plus e minus theta 0 plus theta 1 x. And in this case, we also have a log here. So to calculate this gradient here, we need to consider the derivative of this guy here with respect to theta 0 and with respect to theta 1. And this is just a calculus 1. But in the end, we will see that the gradient ascent we get looks quite similar to the formula we derived for this linear regression. And yeah, but this maybe we will do next time, then also in Python. And the story here is that in contrast to the linear regression, there's no direct formula to solve our problem. So today at the beginning, we talked about this, this linear algebra part where we can find a direct formula for this theta by reducing it to this, this normal equation, to this ATA theta equals ATY. So in this case, we could say the direct formula is we multiply with the inverse. And then this gave a solution here for our linear regression. But this is not possible for this problem here. So here we really need to use some algorithm to find a numerical solution. And this we can either do by this gradient ascent or by some other methods like, so for example, the Newton method. But I think that's all for today.